Okay. We are. Is it sound? Does it sound well? Hello, hello. Does it sound well? Okay, very good. So we are coming to end of the course, and we are expected to do something to have a record of our outstanding achievements. And I hope you will be feeling comfortable with doing another round of presentations based on your independent project. So I will go over all independent projects today as a part of the lecture because I do not want to let you alone, and maybe there are some important questions that are interesting to everyone. So we'll spend some time to discuss projects and what they are, what are under water stones, what should be done or should not be done there. At any rate, please do not have fear. This is very understandable that we have very big projects in a very limited time, and everything cannot be done in a short time. But let's do whatever we can do, whatever is your typical time assignment for this course. If you spend like 2, 3, whatever, 10, 20, 40, but maybe 3 hours per week for the course, just keep spending it and just do your best. So let's discuss administrative part of the course and make arrangements about timing. So we have left. We do have 4 meetings in class and 2 meetings in the lab, right? And then the course will be ended. And what I suggest we do presentations of the final project next Thursday, and I anticipate that we will do it very well. We shouldn't be needing any final to be counted, so that we have finals week more or less free for other courses. I would like to volunteer my own time on Thursday afternoon for additional project meeting in the basement of Arts and Science. It is not obligatory, very optional, but if you feel that you need more time, you want to discuss and maybe sit together, do some computations, I will be happily attending and providing help. So let's try to complete calculations by the end of this weekend and compose our results in form of 2 pages little paper. If everything goes as planned, we will compose them in a little booklet. We can pass it, show to everyone how it should look like after we're done. So the plan is that by next Tuesday, each of us will compose maybe 2 pages report on a project. Then I'm hiring a little local company that will print those booklets by Thursday when it will be time for your presentations. And presenters will be able to follow, attendees will be able to follow the presenter by looking onto the written report. Okay. So I plan to spend maybe half of our meeting, 15, 20, 30 minutes on discussing the independent project. And then in the remaining time, we will keep discussing time-dependent density functional theory. I prepared just maybe 3, 4 slides, not too many of them, can discuss in a freestyle and also look through the last meeting provided by Dr. Huang. And I think due to bad weather, not everyone was able to attend it. So we may go back and look on some slides from previous meeting. Okay. I do have two sets of handouts. So one is a copy from a book. You do not need to read it. It is just an discuss this one and then with one with you and rest to the class. So this is a very good wording and introductory statements about the time-dependent density functional theory, which is a tool to describe interaction with light and optical spectra, the simplest possible way to describe excited state, and is based on density functional theory. The second set of handouts, it is a very short summary of TDDFT equations that you may want if any of you is it is just one page showing what are equations, and if we are planning to use it in our research or in the projects, we may borrow something from here. Okay, so here is the plan, and next Thursday oral presentations, and next Tuesday written report. We will meet tonight, and I will be in the lab on the Thursday. Yes, same time, 6 p.m. I think most of us are busy during the day, and evening time should be better. So there are several projects that you may have selected for your research, and there is absolutely no pressure. You are free to select project you like and do not select project that you do not like. But I have got an idea which projects you are already doing, and let me just show some images of the systems, of the models, and make some comments. What can be done to make it perfect or improve it? So the names near the project are very tentative. I have no control and do not want to have a control of what you are doing, but it is my best guess. So names near the project are just tags. They can be swapped. So, and I do not show any of those projects, only those that really need an attention. So one of the projects is a transitional metal ion in the vicinity of coordination by 6 water molecules. And since transitional metal ions typically take other than neutral oxidation state, the computation of such model should be suited with tags, with number of electrons tags. Otherwise, it will be very realistic. And, it has 2 or 3 electrons. There is a way to avoid this number of electron tags in considering ions of metals, is keeping the model neutral, keeping the total charge 0, as is guessed by, as it is suggested by software. But then one needs to add counter ions. So if one adds ions that are taking minus oxidation state, you can compensate the charge on a metal ion with those counter ions, and then you do not need to use this number of electrons. Of course, if the number of electrons in any part of the system is not even, is odd, then it is much preferred to use spin polarized calculation. There is a project that I do not know if any one of you is taking it, but it should be something big and possible to do in a very in a few hours. But it will be a big experience and help in accumulating skills and growing understanding the concept. So it is a transparent crystal of aluminum oxide with one aluminum replaced with transition metal ion. And if any one of you is interested in pursuing this project, here is a model. You can just take and start playing with it. The one that is doped and one is undoped. And, this model is very does have this model does have a connection to the real world. So this aluminum oxide doped by transition metal ion is the active media in many types of lasers. The one that does have titanium plus in aluminum oxide is this one. Your laser, I think it is of emit light of green color. By looking into this project, the one who is investigating it can get some insight to laser technology. So another project is owned by computational expert who was taking this course last year. So the authorship here belongs to Jeff Pottishaw. So if you will agree to be a leader for one of you, if such collaboration will establish, the first member of this group can investigate the conjugated polymers. But I do not have right to suggest it. The owner and creator of this model is Jeff. If you want to describe conjugated polymer.
Excuse me, Dr. Gillen.
Yes.
Can you pull your mic a little bit closer to your...
Yes, no problem.
Okay.
Is it better?
Yeah.
Okay. So this model is very similar to the titanium dioxide nanowire that we were studying for our practice. One can identify the unit cell and apply this little adjustment. And here, this model is expected to show dispersion, the dependence of energy of HOMO and LUMO and the momentum of an electron. This little exploration of this energy could be enough to complete the project. Arrangements are done in this regard. Okay, so here's one of the projects from the real life. So in case you are taking your academic models from the X-ray diffraction data, which is typically box of very dense periodic structure, then those models are difficult to treat for investigation of excited states and spectra. And if one wants to add a little, be a little bit more versatile, one may want to select only one species, only one molecule out of the whole box, manually remove everything around, save it as coordinate file, then maybe if such molecules interact with metal ions or some other species, they can be added manually in Gauss view. Then in Gaussian one can run TDDFT for reliable absorption spectra. And today in the lab for first 50 minutes, first hour, we will quickly get through how to run TDDFT with Gaussian and how to get very reliable state-of-the-art spectra. This is simple procedure. You did much more complicated things by now. It is really simple step. Okay. Surface of titanium oxide does have some ions that are undercoordinated. So they have less neighbors than same material in the crystalline phase. And it does make sense to compensate the dangling bonds there by a solvent. And it is not theoretical or artificial practical assignment. It is what typically happens in real life. So if the surface is exposed, it attracts some ligands in a solvent, or it attracts the humid from the air, and those surface ions are getting their preferred coordination. One of the
Excuse
projects.
me.
Yes.
I have a question on this one. If you are.
Yes, please. Yes.
I had a structure of TiO2 in postcard.xyz file. I converted. I kind of opened it on Gauss view and added some CS3CN molecules
Yes.
near to it, and then converted it to PDV file. I guess, and then to XYZ. Later, when I opened that file in JMOL, the CS3CN molecule were attached with this TiO2 structure. I don't know why they are like. I haven't processed it. I have just converted the file type, and I found that when I opened them in like JMOL, they are kind of attached with this TiO2 structure. Why is that?
What does it perturb? Does it break the TiO2 structure, or
No, it didn't break. They are just attached on the surface. They are kind of bonded.
Okay.
It didn't change the crystalline structure of TiO2 structure, but they are kind of bonding on the surface with TiO2. Is that
It is okay. Well,
expected?
you need to optimize the structure and let the system to find best interatomic distances, and it is generally it is a challenging task. One needs to set up very little TO time equals something 0.000, very little number. If you draw something by hand and use a big number for this tag, the system may explode and show that all ions will just fly in different directions, and model will be completely corrupt. But before any analysis, one needs to optimize the structure with using in-car geometry optimization.
Yeah, I'm doing this, but due to the structure size, it's taking me like days and days. I don't know how to do it. I have like
Send me the directory where you do it, and we'll discuss it by email.
Okay.
Send me the directory, link to the directory where it is. Okay.
Okay, I'll send you that link.
Okay, good.
Thanks.
So we already had a discussion on this model. Here is the directory where this structure is residing. And another possible project that has a very big chance for success and being related to real life is the model of semiconductor with P and N doping, where this this structure is periodic in all three directions, X, Y, and Z. And it does have a region that has aluminum doping and has a region that is doped by an alternative phosphorus doping, which adds additional electrons. So this is N, this is P. And just looking on this electronic structure of this model, one could get some interesting insights, and it is more than enough for research project. Okay, so this was a little overview. If the project that is not here in this list, it means that you are in a very good standing and probably everything is straightforward. So let's look onto the time-dependent density functional theory. So I hope that you are already moving forward in understanding this theory to the big extent that you went far enough. But let's discuss. Let's start discussion from the very initial point. So, what is time-dependent density functional theory, and why do we need it? So, based on the whole course, or third chapter of the course, we do know that regular ground state density functional theory does provide helpful insights into the chemical properties when system is not perturbed, when it is in the ground state. And not technologically, algorithmically, the density functional theory, based on the fact that density determines energy. Density of electrons in the ground state determines total energy of the electronic system, also in a ground state. This is very good and very helpful if the system is isolated from external perturbation. But one of the powerful, useful, helpful, and popular tool to probe properties of materials is associated with perturbing materials, perturbing models with electromagnetic radiation. Maybe some other ways of perturbing system also do exist. So the system can be affected by shaking, by irradiating, by applying fields, and definitely one is expecting that applying those external fields, especially if their intensity does change in time, will modify the total energy and will modify the density. Apply external field. And consider how the external field perturb these two key features of the density functional theory: density and energy. So generally, if the system is being perturbed, if this perturbation is function of time, if it is non-stationary, then one is not allowed to use time-independent Schrödinger equation. We know all this stuff about DFT is not Hamiltonian, is not using Schrödinger equation, but as a tool, it does use Kohn-Sham single orbital equation for orbitals. And it is analogous to time-independent Schrödinger equation, which is okay for ground state. But as soon as we start perturbing system, it is not legitimate anymore to use time-independent picture. with these perturbations, time independent Schrödinger equation isn't valid. So we do need to use the time-dependent form of Schrödinger equation, or analog of this time-dependent Schrödinger equation, even if we are in the frame of density functional theory. So the designers of the TDDFT did pose for themselves a task to project concepts of the time-dependent Schrödinger equation to the density functional theory, so to add dependence on time. And therefore, the density that was time independent, originally the density was depending only on position. Now it does depend on time. If you want to describe these models in a precise, rigorous way, we do need to track the reason, track the origin of this perturbation. And we need to understand where the non-stationary nature of this effect come from. Our typical molecular Hamiltonians are time independent. So why do we get any time dependence? Where are they coming from? We are not going to challenge the building of science. We are not going to introduce any new concept. We are going to just utilize whatever is available to us. So we are going to speak on the language of molecular Hamiltonian, total density, Schrödinger equations, functional derivatives. So no new concept, just accumulating the dependence on time within this frame. So the perturbation, the time-dependent part, comes first to Hamiltonian. So total molecular Hamiltonian can be written as the one for ground state plus some perturbation which is time-dependent. Time for perturbation does depend on time. So all these considerations can be done in the situation when our Hamiltonian, our molecular Hamiltonian, is not complete anymore. When there are some external processes that modify the Hamiltonian, and those processes, these modifications of Hamiltonian, are not stationary when they do depend on time. So in this case, in the case of time dependence of the Hamiltonian, the density depends on position and time will be equal to density in the ground state plus perturbative density that does depend on time. So the solution of this problem, if it does exist, should return back to ground state property as soon as we remove this time-dependent part. If you remove this one should also disappear. And we should get back into standard time-independent density functional theory. This is assumed to work when those perturbations are small. And the key component, key characteristic of the density functional theory is energy. So we expect that total energy in case of this perturbation will change to energy total ground state plus something else, some perturbative component. Maybe it is time dependent, maybe not, but some addition to the total energy should appear due to perturbative Hamiltonian and perturbative component to the density. Any questions at this point? Any objections? No, not yet. By now you already know the time-dependent density functional theory. This was a major introductory step that gives an understanding what it is. The rest are mathematical technicality. Okay, so I already wrote it. I was planning to write equations myself. Okay, so then I will just go through lines. So the simplest situation, and scientists try to track simplest situation first, right? The simplest situation of perturbation is when it does depend on time in a harmonic way. When some external field appears, disappears with some period, with some frequency. And then, if the perturbation is harmonic with only one selected frequency, then all three key components are assumed to follow the signatures of this frequency. So Hamiltonian, the perturbative part of Hamiltonian will oscillate with this frequency. The density will also have a contribution that oscillate with this frequency. And energy will also have a trace of this frequency in some different way. So most popular, most practical example is when this time-dependent perturbation corresponds to electric field that changes in time. This is transition dipole operator of a molecule of the material. Right. So then this dipole times field is energy of light to matter interaction in the dipole approximation. Okay. So change of Hamiltonian will be reflected in change of density, and this density will have a component, the amplitude, that oscillates with this frequency. So the one important intellectual effort that was done by developers of the theory, the TDDFT, is that one is referring to this theory as time dependent, but if you run it with some software, like Gaussian software, you do not see any time dependence. So this keyword is a little deceptive. You say, oh, I'm running time-dependent density functional theory, and a site listener can ask, okay, show me your time dependence. I do not have time dependence. So this is because one assumes that time dependence is very simple, and instead of working with this part, which does have time, one works with amplitude. So one writes equations for amplitudes of those periodic changes of the density. So this time dependence is in our heads. We understand that it is behind the theory, but we do not have it in explicit equations. And this time dependence is not in the code, is not in the output of the when we run the code. So actual output of computation is time independent because it is computed for amplitude. I don't know how to verbalize it. So we do have a paradox. Our time-dependent theory gives time-independent results. Theory gives independent results. Okay. Very good. So we agreed on 2 points, on 2 steps. First, that time dependence is needed to describe external perturbation, and second, that it can be time dependence can be excluded from the explicit consideration because we assume that it is takes place in a very simple form. We understand that it is there, it describes the time-dependent perturbations, but we excluded it from equations, from computation. Here, we may set up a question of mathematical spectroscopy, if I can say so. So the system can be perturbed by oscillations, by time-dependent perturbations of different frequencies. At each different external frequency, system will be perturbed in a different way, meaning that we can shine light of different frequency, of different wavelengths. And at different wavelengths, system will be perturbed in a different way. For some frequencies, it will be very responsive. The irradiation of one frequency may launch chemical reaction or be absorbed in the material. And for some frequencies, material can be transparent. Light just passes through it, right? So this feature is what we need to treat more or less rigorously and what has been put into the algorithm for time-dependent density functional theory. So the frequency of this perturbation determines the amplitude of this change in density. And actually, this frequency of perturbation is also provides change in total energy. So those amplitudes of the oscillating component in the density do depend on frequency. Any questions or points of disagreement at this point? No. Okay. So in a silly way, we may think about establishing procedure analogous to actual spectroscopic experiment. We are trying different frequencies and looking onto the response of the model at each frequency. Just going the whole spectral range. Instead, it was possible to establish an equation that is naturally coming from density functional theory that provides as a solution a list of frequencies for a given material, a list of frequencies which do interact with light, which at the frequencies at which the material has a strongest response. And this set of frequencies is discrete, and the code is set up in a such way that they are counted from lowest to highest frequency. So the mathematical goal for time-dependent density functional theory is to find such frequencies which provide maximal response, maximal amplitude. For this perturbative component of density. So it is a brief answer of what we are getting from time-dependent density functional theory calculation. We are getting set of frequencies, and those are excitation frequencies at which system can be excited. Okay, and in addition, we are also getting those amplitudes of oscillating density. So there is a eigenvalue problem that provides frequencies and eigenvectors, and those eigenvectors are amplitudes of density. Another, wait, okay, let me just add a couple of empty slides. Okay, so the goal of TDDFT is to find a set of frequencies which provide maximal response for perturbative density. And the practical component or practical use of those solutions is that based on this information, if it has been found, one can immediately, with very simple connection, one can compute reliable enough absorption spectra of material. So the absorption spectra are typically computed as oscillator strength component times difference between energy and transition energy. So we are looking for converting the information that comes out of TDDFT and feed it into computing of absorption spectra. So we do have those frequencies right away. And tonight, starting at 6 and being done with this part at 7, we will see how those frequencies are coming out of the running Gaussian. In addition, those transition densities can be used to compute the oscillator strengths. And you probably have an idea that oscillator strengths can be computed as square of transition dipole times some constants. Now we are not focusing on those constants. This transition density dipole station element can be expressed based on the transition density. So we do have the old way to compute matrix elements, and now we are going to look on a new way on computing matrix elements. In the old way, one is using the pair of orbitals, operator, orbital integration. Right? In the new way to compute matrix elements is to perform the trace operation of operator times density. So these two operations give the same observable, but the first one is applicable to one electron picture, and this one is applicable to a picture of transition density. So through TDDFT procedure, one is obtaining frequencies and this amplitudes of perturbative density, right? And these two components are needed to compute absorption spectra. So the absorption spectra are composed of frequencies and oscillator strength. And oscillator strengths rely on the expectation values of the transition dipole operator. I'm going to jump back on the previous slide. So this is an observable that can be compared to experiment. Oscillator strengths, frequency. Oscillator strengths is computed based on the metric element of transition dipole. And dipole is computed based on the amplitude of densities that come out of TDDFT. Let's probably summarize it in a sort of flow chart. We end up with spectrum. We need the frequencies and oscillator strengths. for oscillator strengths, we need transition dipole matrix element, and transition dipole matrix element can be computed from the amplitude of perturbative transition density. So this is kind of oversimplified way what is TDDFT and what one can get out of it. And, this little flow chart is a list of outputs. This is what one can get output of TDDFT. What do we need as an input? Where we start from? So for any computation, one needs a set of positions of ions, total charge, standard things. In addition, one does need a number of how many of those transition energies we need. So as an input, the non-standard input, one needs to know the number of requested transition energies. So the speed, the rate, the numerical expense of computation strongly depend on this number. On one side, so ordering, requesting too many of those transitions, one get slower computation, longer time. On the other side, the number of those transitions does determine how precise your spectrum is. First frequency, second frequency, third frequency. Then you can expand your absorption spectrum maybe to some limited number, to 2 volts. If you order typical numbers are maybe 40, 50, 100 transitions. So with having more of those frequencies, one can expand to complete visible range and maybe a little bit to UV. But this is possible for smaller molecules. If your molecule or material has a lot of ions, then in order to describe the whole visible range, you need a lot of those transitions. And then computation gets expensive. So we did discuss this take-home academic part of the meeting. So we went from ground state density functional theory to perturbations. We removed the time dependence. We remove the time dependence by assuming that it is in a very simple form. Then we do believe that there are some equations, main equation of TDDFT, which provides set of frequencies and set of transition density. And in order to run the computational software, we need to know the number of those transitions. So our last truly academic lecture will be on coming Thursday, and we will discuss where this equation is coming from. I think you have already discussed it in last week, but we will go over once again, and this will complete the theoretical part of the course. So with this, I would like to announce end of the lecture. It should be 26 or 27. And with this, I'm ready to answer any questions or announce the end of the meeting. Okay. So if there are no more, generally no questions, then thank you for coming, and see you today at 6.